All right, we're going to talk today about the rational roots theorem. So the rational roots theorem helps us factor equations. Let's say we have something like this: x squared plus 6x plus 8. If we wanted to factor this, we know that the number here and the number here, when I multiply those two numbers together, I need to get this number 8. So that gives us a few possibilities, and usually we write them out like this: 1 and 8, 2 and 4, -1, -8, -2, -4. And we would test these different possibilities and see which one would work. Now, the same thing happens for a third degree polynomial. X to the third plus 6x squared plus 5x plus 8. Now, because this one is a third degree polynomial, that means we would have 3 sets of parentheses. And then this number times this number times this number would have to multiply together to be 8. So when I'm considering the numbers to put in the factors, it might be something like plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. For example, maybe this polynomial is x plus 1, x plus 1, x plus 8. Because if we multiply that all across, 1 times 8 would give us that 8. Now you have to multiply that out and see if it was that whole polynomial. But we could also try this possibility: x plus 2, x plus 4, x plus 1. And if I multiply that together, then maybe it would be the whole polynomial. Certainly I would get the 8 at the end. You'd have to check and see if you got the 6x and 6x squared and the 5x. So it turns out that it's really difficult to factor polynomials. X to the fourth plus 5x cubed plus 3x squared minus x plus 7. I just randomly chose those coefficients, and I know, because it's a fourth degree, that it will have 4 factors. But I don't know what numbers will go in here. It might be something really nice like this. Or it might be something completely weird, like the square root of 7 over pi, or something equally weird or confusing. We don't really know right now what it'll be. It could be something like this. Or it could be x minus 2 plus the square root of 7 over 5. We don't know what those are going to be. And it's just really hard to factor these types of things. And so to limit our choices that we have to run through, that's where the rational roots theorem comes into play. We know that this last number is a 7. So that means in my first example, I know it can't be this case, because if I multiply those guys across, I'm not going to get 7. And so it helps us know that if it has rational roots, it might be something like this, because that gives me that last number 7. -1 times -7 is positive 7, and then that'll give me a positive 7 at the end. So the rational roots theorem is a way of generalizing this, and this is how the theorem goes. So the rational roots theorem, it says if you have a polynomial a x to the some power plus ... something x to the something, and at the very end you have b. So if you have this polynomial and a and b and all the other coefficients are all integers, so if all of the coefficients are integers, then what the rational roots theorem tells you is that the values that make a 0, the values that help you factor it, have to be in the form. So the zeros, I'm going to say the rational zeros, if they exist, and again, they might not exist, but the rational zeros, if they exist, are in the form factor of b over factor of a with a plus and minus. Okay, so let's go through an example. If you have x squared plus 6x plus 8, then the values that make a 0, the values that help you factor it, are going to be factors of 8. Factors of 8 are 1, 2, 4, 8, over the factors of 1, which is just 1 with a plus and minus. So that means it could be plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8. So it could be something like x plus 1, x plus 8, or it could be x plus 2, x plus 4, or it could be x minus 2, x minus 4. But those are the possibilities we'd have to consider, and I wouldn't need to consider the possibility that, for example, it could be x plus 7, x plus something, because when I multiply those out, we're not going to get the 8. So this tells you that when you're trying to figure out the factors, you can limit it to the things that multiply to be that. Let's do another one that's kind of more of a test question that you're going to see on a test. You're going to have 3x to the 6 plus a bunch of stuff. At the very end, let's say you have 5. So we're going to list all the factors of this one. So the rational roots theorem says list all the factors of this one on top. So that's going to be 1, that's going to be 5. All the factors of this on the bottom could be 1 and 3, plus and a minus. So it means you could have 1 over 1, 5 over 3. You could also have 5 over 1. You could also have 1 over 3, and plus minus, plus minus, plus minus, plus minus. So simplifying a little bit, you have plus and minus 1, plus and minus 5/3, plus and minus 5, and plus and minus 1/3. Those are all the possible rational roots. So if you are factoring 3x to the 6 plus something something 5, then if I was using synthetic division, those are the ones that I would try. I would try dividing it by an x minus 1. If that doesn't work, try dividing by x plus 1. If that doesn't work, try dividing it by x plus 5/3, and so on and so forth. Try all those possibilities, and if none of those possibilities work, then we can say that this equation has no rational roots. In other words, its roots might be something like x plus the square root of something, x minus the square root of something, x plus I, x minus I, but things that are not rational. If they are rational, then they are included in our list that we produced right there. Okay, one more example. This one, do on your own. Let's say we've got x to the 6. Let's do 4 plus something, 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 and we'll do 9 at the end. Okay, so if this equation has rational roots, they're going to be in the form of factors of 9, 1, 3, 9, over factors of 4, 1, 2, 4, with a plus and minus. So that could be 1 plus and minus, okay, 1 over 1, or it could be 3 plus and minus, it could be 9, or it could be 1/2 plus and minus, it could be plus and minus 1/4, or it could be plus and minus 3/2, plus and minus 3/4, it could be plus and minus 9/2, plus and minus 9/4. And I think I got all of them, but you'd have to go back and check that these are all the possibilities you could get from that. Okay, that's it.